This lecture discusses the sampling distribution of differences between the means, and as is discussed in the textbook, a sampling distribution is a frequency distribution of differences between sample means, and the mean of this distribution is 0. It assumes that there is no difference between the two groups. And the sampling distribution, just like other sampling distributions that we've learned about, is a standard curve. So it's bell-shaped, it's symmetrical, and it's unimodal. And just like other standard curves, we can assign percentiles and areas to specific points on that axis. So this is just to illustrate, this is a figure that's taken straight from your book, figure 7.1, to illustrate the mean difference in permissiveness between samples of males and females taken from a hypothetical population. This overall circle refers to the entire population of men and women that could be chosen. And this circle here represents either the men or the women, and this circle represents, let's say, that this is the men. And what we observe is the difference between them. So the average permissiveness score for this sample of women is 58, and the average permissiveness score that we observe from the men in this sample is 54. And if I subtract the two average, I get an average difference of 4. But if I kind of up that to the sampling distribution, here I have a distribution of 70 mean difference scores. Okay, so here, for example, is the observed score from the previous slide. Remember, okay, the observed mean difference that I had in that sample was 4, and now my observed sample could be, for example, -2. Okay? The idea is that each score represents a mean difference between a sample of 30 females and a sample of 30 males. So that's my sampling distribution of the difference between the two means. If I look at this in terms of a frequency polygon, I can see that on average, okay, assuming that the null hypothesis is true and that there are no mean differences between men and women in their permissiveness rating, then the mean of that distribution is going to be 0. But as I graph the observed scores here, okay, if I graph all of these observed scores, I'm going to have a spread of scores around this 0. So if I go back here, I can look to see, how many times I observed no difference. Okay, so here I have all of these zeros. Remember that this is a hypothetical distribution. But the point is that the majority of the time I observe no mean differences. Okay, when I plot this on a frequency polygon, I can see that in general, okay, the typical distance or the typical difference between men and women in this hypothetical sampling distribution of differences between the mean is 0, but that I have observed mean differences that vary significantly from that 0 point. The point is that once I start testing hypotheses, I draw one pair of samples. Like if I draw a training group 1 and training group 2. If there is a difference, okay, that I observe, I infer that there's a difference between those groups that's based on the training group. And then to evaluate whether or not that difference is due to sampling error or more than sampling error, I use column C of table A, which gives me my significance levels. And this tells me whether or not my result is statistically significant. So remember that what we're doing with hypothesis testing is we're comparing an observed ratio to a critical value. And those critical values are what's listed in column C of table A.